Hi, we will wait for 2 minutes to everyone to join and then we'll start today's session. So, hi everyone, myself Umesh Shule. I am a PMRF student in the Department of Civil Engineering IIT Madras, and I am handling NPTEL TA sessions for the design of reinforced concrete structures. So, we'll see today about the design of reinforced concrete structures, and basically in that uh, we were looking for design of doubly reinforced beam in flexure. So I would like to ask, what is the requirement of design of the doubly reinforcement beam? First of all, let clarify what is doubly reinforced beam. So anyone knows what is the doubly reinforced beam? Abhijit, you know, or shall I continue? Okay, I will continue. So the design of doubly reinforced beam, in that a doubly reinforced beam means that the steel is in both the zones. What are the both the zones? The zones like compression zone and tension zone. Just a minute. See this. This is compression zone and this is tension zone. So in both the section, if there is a steel, that then we call as a doubly reinforcement beam. So what is the requirement of designing the doubly reinforcement beam? So the requirement is like depth is constraint. What is the depth is constraint? Like, can you see here? Can you see this depth? If this depth we can't increase behind some depth, like for example, for the architectural point of view, and there is a constraint in the depth and we can't increase much. So at that point of time, we have to go with the whatever the depth is we have like is allowed. So in that case, we can design the beam by considering doubly reinforcement beam, and we can consider like we can design the beam where the steel is in the tension zone and in the compression zone also. So here you can see that here you guys can see that the ASC means the area of steel in compression, AST means area of steel in tension, and this we can split it in such a way that AST1 and AST2 plus ASC. What is ASC? ASC is the steel which is provided in a compression zone, and by this we can tell that AST total area requirement is AST1 plus AST2, and we can design in such a way that we can design the doubly reinforcement beam in such a way. We will see this in the next upcoming slides. So the analysis of W reinforcement sections, like basic considerations are: RC section in a bending fails when the compression strain in the concrete reaches its value of 0.035. You can see it here. If this value is reached in a concrete zone, then we can say that the RC section bending fails. So that is the consideration is there in the W reinforcement beam, and the plane section remains plane even after bending, that is there. So, and also the other requirement of the W reinforcement beams are moment of resistance required is high. Like in some section, if there are a lot of high intensity loads are coming, that time we want a little bit stronger beam to be designed. So by designing like a W reinforcement beam, we can have the high moment of resistance in that beam. Also, in a continuous beam where there is a moving load on a continuous beam, and because of the moving load at the support section, there will be changes in the nature of the loads, like as we see that tension is in the bottom side and the compression is on the top side, but due to the moving load it can reverse its signs. So if it is reverse its size, then on the top section where it is only concrete is there, if you consider the single reinforcement beam, so it can't take the tension. So to take that tension which is coming due to the moving load, we are designing a W reinforcement beams. So that reinforcement, what that is ASC, that will take the reverse forces which are coming due to the moving load. This is generally happens on the continuous beam, like in a bridges, if it is designed as a continuous beam. Okay, so we will see the steps to design it, and then we will solve the problems. So the analysis of W reinforcement beam, as we know, see here there are steel is in the compression zone also and the tension zone also. The total depth is the D, and the D dash is the clear cover at the compression zone, and we can find it out the lever arms. Like CS is the compressive forces in the steel area. CC is the compression forces in a concrete, which is typically we see in a normal design of the single reinforcement beam, and T is the forces in the tension steel. So ZC is like a lever arm of the between the compression forces in the concrete and the tension in the steel, and the D minus D dash, which is the distance between tension steel and the compression steel, we can say compression steel also we can say. So D dash we can calculate like a clear cover plus 5/2, as we know, because we want the cover from the center of the steel to the outermost layer of the concrete. So it will be calculated like this. So total force in the concrete can be calculated as a CC plus CS, like you can see it here. These two addition will be total compressive forces. So how we calculate CC is directly by KFCK BD square. That is for typically we know that formula, we directly calculate. How we calculate EMU? EMU we can calculate total EMU, we can calculate CC into ZC, and the CS into D minus D dash, CS into D minus D dash, because there is a compression steel section is also added, so this term is also added. Otherwise in the normal section only this first term will be there. So here also you can see that like K values you can directly put for a different grade of steel, and we can directly calculate. Here you can see that for the FCK FE415 it is 0.138 FCK BD square. Directly we can calculate the EMU limiting. So how to calculate the strains in a compression steel. So for that, directly this is the formula. By similarity of triangle, ES is can be calculated as like this. Considering that XU is like it is a maximum, X becomes maximum, then it will be D by 2. So by solving that, D dash divided by D will be 0.2. So it should be always greater than this, because the minimum strain is in the steel A should be greater than or equal to 0.002. That we already have seen, and XU by D is 0.4. By solving that, we get 0.2. Okay. Also, the strains and stresses in the steels are given in the IS codes, and here professor have written it. Like for 0.8 of yield strain, what is the strain and what is the stress, he directly have given it. And whatever the strain is coming in our problem, we have to find it out by using if it is between these two, we have to solve it by proportioning it. So for the Fe500 also it is given. Also, yeah, we know that the mu limiting we can calculate by these formulas for the different grade, and then we can calculate the balance steel requirement. For that also there is a direct formula, PT, like this also you can directly remember it. Like for the 250, Fe250 it is 21.91, for 415 it is 19.81, and for 500 it is 18.87. That is FCK by Fy. Directly you can get the percentage of steel in a balance section. Okay, and there are other way also to solve it, but this is one of the way professor have adopted. And the AST, we know that it is equal to PT into BD divided by 100. So we can direct from the percentage of the steel, we can directly calculate the AST. Okay. So determine the stresses in the compression steel. Like CS, how to determine the CS? CS is directly FSC, which is the stresses in a steel minus stresses in a concrete. Okay. So for that, professor have mentioned that we can neglect FCC because it is very less value. Like you can see it here, 0.45 FCK is the value we put for FCC for the M20 grade. So it is coming around 9. But FSC is coming around 0.87 Fy, which is around 361. So the difference will be very like it will not change much. So directly we can calculate CS as a FSC into ASC. Okay, CS, which is this CS. So for calculating mu2, the additional movement in the compression failure due to the compression steel, that we can calculate by now FSC into ASC. Here we have ASC, and by putting FSC and ASC, D minus D dash, directly we can get the mu2. And total mu is like mu plus mu2. So mu2 is like FSC into AS into D minus D dash, that is written here, and mu1, which is calculated for the balanced steel section, which is here mu1. That is direct formula available. Okay, for the different grade of steel. You guys can remember the 0.13 FCK BD square, because most of the time the problems are asked from Fe415. Yeah. So find the total mu for the tension failure, considering the final failure to be due to the tension steel reaching the yield, by considering that mut is equal to mu1 plus AST2 0.87 Fy into D minus D dash. That is, we have written it there because we are considering it that to be yielded. And from MUC, which is in a concrete due to the concrete, and MUT is due to the tension, we have to select the minimum of this, because it is analysis, and in that we will report whichever the moment of resistance, whichever is the lower. because if that movement is coming on the beam, it will be in the safer side. And if we mention the higher one, then it can fail, because it can fail in a compression also. If considered compression MUC is lesser than MUT, by considering it, for example, by considering it can happen, so we will always report the minimum one. But for the design one, we will design it for the uh, for the de- for the design purpose. We will always design the beam for having the highest movement coming. Okay, so now we can take the problems, and then you guys can uh, try to solve the problems, and we will understand it from the problems directly. Okay, so the first problem, as you can see it on screen, is like the reinforced concrete beam 230 mm wide and 430 mm effective depth. Directly they have given the effective depth is provided with the M20 grade of concrete and Fe415 grade of steel. Typically these grades are given. The beam has to resist the three different design moments: 90, 117 and 140 kilonewton per meter. Find for which bending moment the beam will design as a singly reinforced or doubly reinforced section. Okay, so that we have to design. I will give the hint, like we have to calculate the EMU limiting, and we have to consider the EMU limiting to whatever the moments are given. If our MU limiting is greater than the moment here it is given, then it will be different type of design, and if it is greater than that, then it will be different type of design. That you have to answer. Considering it, let's consider. Okay, you try first, and then we will see. Then we will discuss. Okay, anyone with the answer, or shall I provide the hint? Okay, consider the hint as, let's say whatever the they have given, whatever the parameter, our our movement limiting movement is coming as 115. Let's say for an example, I am saying, I have not solved it, so the answer is in the next slide. So but let's consider it. Okay, so how we will calculate, how we will design 90 kilonewton, what on the moment where the 90 kilonewton is coming, where our MU limiting is 115. Okay, so 90 is less than 115. So what will be the design? Let's consider it is as a 117 for simplicity. We are considering 117. So the 90 is less than 117 kilonewton. So it will be designed as a singly reinforcement, because it is because the MU limiting is enough to provide safety, as it is coming less than the MU limiting. But when it is 117, then we have to design as a balanced one, and if it is more than 117, then obviously we have to design as a doubly reinforcement section, because whatever the MU limiting is there, it is not sufficient to provide the moment of resistance to whatever the moment is coming on the beam. Okay, let's see the answer. Okay, in solution, like width of beam is 230, effective depth of beam is 430, directly it is given, FCK is given, Fy is given. So the MU limiting direct formula is there, you guys can remember it, 0.36 XU by XU max by D in bracket 1 minus 0.2 XU max by D in BD square FCK. So when we put XU max by D in as a 0.48, it will become 0.38 FCK BD square, that we already have discussed it here, right? These are the formulas. Okay, so this is XU limiting. Okay, so this is coming to be by calculating it is coming to be 117 kilonewton meter. So as 90 is less than that, the section will be designed as a singly RC beam and under reinforced section. Okay, and since 117, the section will be designed as a singly RC beam only as a balanced section. But since 140 is greater than 117, the section will be designed as a double reinforcement beam, where there is a requirement of steel in a compression zone also. But do you guys know that most of the beams we design as a doubly singly reinforcement, but at the site we always provide some amount of steel in a compression zone. Why is that? Like always we provide it. Why is that? Anyone knows? Okay, we will discuss this and then we will move forward. So this is the beam. In practice we always provide the steel at the bottom and at the top also. Why is that so? Even the compression steel is not required, still we provide like that. So the answer for this is like, anyone want to try? So answer for this is like to hold the stirrups. There are the stirrups also in the beam, right, to resist the shear, that we will see in some next classes. So this stirrups is held by the top bars and the bottom bars. For that we always provide the steel in the compression zone also. So yeah, so it's better practice also, because our beam is always safely designed. Okay, so the next problem, we will go to the next problem. The problem number 2 is a doubly reinforced beam. 1 minute. A doubly reinforced rectangle concrete beam has a width of 300 and the effective depth of 500. The beam is reinforced with the 1600 mm square of the steel in a tension and the 628 of steel in a compression. Directly they have given ASC and AST also. The effective cover for the compression steel is 50 mm, and assume that both the tension and compression steel yields. The grade of concrete of the steel used are concrete and steel is M1210 Fe415 typically. Then setting the value of FSC also they have provided. The value of FSC also they have provided. We don't have to calculate by considering the this we don't have to use this table to directly calculate the stresses at whatever the strain coming in the FSC. So directly they have given these values, so it is easy problem, I guess. So yeah, FSC is also given. Determine the depth of neutral axis and a moment of resistance of the beam. So the maximum MR we have to calculate, and the neutral axis also. That is the question. Please try to solve it, and then we will see the answer. वीडियो में आ जाएगा वो वीडियो बंद है ना निकालो सो anyone got the neutral axis anyone? Okay, we will move forward and we will see what is the neutral axis first, and then what is the moment of resistance of the given beam. Okay, so depth of neutral axis, we know that force of compression equal to force of compression. No, this is force of compression equal to total force of tension. So that's wrong. So force of compression in a concrete plus force of compression in a compression steel is equal to force of tension in a tensile steel. Yeah, that's correct. That also we have seen in the previous slides. So we will calculate by this formula 0.36 FCK BXU plus ASC into FSC into FCC and 0.87 FY AST. Directly putting it, we will get the neutral axis. So this is the neutral axis. This formula you guys can directly remember. This is for the doubly reinforcement beam. So in the lecture by professor, in that he has mentioned that FCC we can neglect it because it will be very less value, as you can see it here also. 0.445 into 12T, which is very less value, is around 9 with the consideration of 351. So that we can neglect also, but it's okay. Like you can consider it and calculate the XU. So this is the neutral axis, we got it. So the limiting depth of neutral axis XU max in this section, because we have Fe415, it will be 0.48 into, sorry, we have yeah, so we will get XU max by D is equal to 0.48. Okay, so by that XU max will be 240. So as XU is less than XU max, the section is under reinforced. Okay, so it's not over reinforced, it's under reinforced. So the total moment of resistance mu we can directly calculate by this formula, 0.36 XU by D in bracket 1 minus 0.42 xu by d into bd square fck. That is the first formula, and this is for the compression one, right? The first one, before this plus, that is for the that is normal formula we already have seen, and this is the addition one for the compression steel, that is ASC in bracket FSC minus FCC into D minus D dash. That this is you guys can directly remember for fast solving in the paper, and by calculation directly we got the moment of 252.5 kilonewton per meter. So that is the moment of resistance for this provided beam. Okay, so the problem is solved. We will move forward to the next problem. Any problem in this any problem in understanding this solution, or shall I repeat? For calculating XU, which is the neutral axis, directly there is a formula, which is this formula. We have used this formula. We know FCK, we don't know XU. We know all ASC and FSC, FCC, AST and FY. So directly we have put that in a formula and we have solved it. Okay, let's move forward to the next question. The problem number 3, a doubly RCV beam 230 mm wide and the effective depth of 450, and the beam is reinforced with the 2 into 16 mm dia in the compression zone, and 4 into the hash means 4 bars and 12 mm dia, that is they have given diameter in the tension zone, with a clear cover of 25 mm for both the steels, compression and the tension steel. So calculate the depth of the lever arm for the force of compression for both the compression steel and the concrete. Yes. So, and also find the moment of resistance, flexure capacity of the beam section. Assume M20 grade and Fe 415 grade of steel. So it is a similar problem like whatever we have solved in the previous one. So just little bit different, but it is a similar one. Try to solve it and then we will see the answer. Like we have to calculate the area in the previous problem. Directly the area was given, so it is easy to calculate the area, like they have given the number of bars and the diameter also we can calculate. Effective depth directly they are given, and the width also they have given, so it's easy problem. Okay, I will wait for 2-3 minutes and then we will see the answer. Okay, let's see the answer and then we will discuss about it. Okay, so the given we already know, and then we have calculated the area of ASC and AST. Moment of resistance for the singly RC beam, that directly we can calculate, as also we have discussed in limiting 0.36 XU max by D and 1 minus 0.42 XU by D into AD square FCK. So by putting that we will get the MV limiting for the singly RC, that is 128.45 into 10 to 6 Newton per meter. So the area of the steel for the singly RC, that we can directly calculate by using this formula. A professor have used percentage of the steel approach to calculate it, but there is one more way to do it. Like this is a direct formula for the calculating area of steel in the singly reinforced RC beam. You can directly put all the parameters and directly calculate the AST. So we have put all the values as we know, because we have calculated earlier, and then we got the AST1. By that we can calculate the AST2 also. So the lever arm for the force of compression for the concrete, this is Z1, which is like a lever arm for the like a normal beam where the compression forces are applied in the concrete zone and the tension forces are applied in the steel. For that the lever arm is D minus 0.42 XU max, that we can directly calculate here. And the lever arm for the force compression for the compression steel, that is because of the extra steel we have provided in the compression zone, that we can directly calculate as a D minus D dash. I will show you that in the slides we have already discussed. You guys can see it here, like ZS is like D minus D dash, which is the lever arm for the CS, like the extra steel provided, and ZC is like the normal lever arm, which is like a D minus 0.42 XU max. Okay, so where we are, problem number 3. So then this also we have discussed. So the lever arm also we have calculated now. So and the effective depth you can directly calculate, effective depth minus the top clear cover in minus 1/2 diameter of compression bar, that we can directly calculate here. So the remaining area of the steel AST2 is like AST total minus AST1. Total we know that it is 1256 and minus whatever we have calculated at AST1, which is here. Then we can calculate the AST2. Okay, so the corresponding value of FCC and FSC we can directly calculate it. FCC is like 0.44 into FCK, which is I already told it is around 9, and which is very less, and we can neglect that. And FSC is like 0.87 FY, which is 361. So the additional moment of resistance mu2 is like ASC FSC minus FCC into D minus D dash, that we already have seen. So ASC we have already calculated, so which is here. ASC you can see it here, and this is like total AST, and by putting in this formula we got the additional moment of resistance, which is mu2. So total moment of resistance of WRC is like the mu1 plus mu2, then this 59 plus the previous one which we have calculated here, that is 128. By adding both we will get the total moment of resistance. So this one is the moment of resistance that the given beam can carry. Okay, so this is the design for the doubly reinforcement beam. Okay, any problem in this for understanding any, like The formula which is used by professors are little bit different than here. As per your convenience, you can use these formulas or whatever the formulas followed by professor also you can use that. Both are okay to use. Okay, so we will see the problem number 4 and then we will close today's session. So this is the last problem. Try to solve it by yourself and then we will see the answer. The problem is design the reinforcement of this simply supported rectangular RC beam having the span of 6 meter and the beam is subjected to uniform distribution load of 25 kN per meter over the whole span, and the size of the beam is restricted to 250 into 500 with the effective cover of the reinforcement is 40. Take FSC equal to 353 and the M12T concrete and Fe415 steel are used. So here the depth of beam is restricted. We have to check it if it is, we can design it as a single reinforcement. If that is not possible, then we have to go for double reinforced. So that is the catch in this question, and then try to solve it. The only changes in this is that for every time the directly moment of resistance was given, but in this we have to calculate the loads coming onto the beam and then what is the moment which will be coming onto the beam, and then that moment can we resist it by providing a singly reinforced, or we have to go for doubly reinforced, that we have to check. Okay, so I will give 3-4 minutes just to solve and then we will discuss. Okay, so let's see the answer and then we will try to learn it, how this type of problem can be solved. So yeah, so whatever the dead load they have given, no, we have to calculate the dead load, which will be uh, the volume of the beam into the unit area of the concrete and steel together. So that we can calculate per meter, we can calculate as a B into total depth into density. So density is 25. So by putting that, we will get that is this is the dead load, and superimposed load directly they have given as a UDL. So directly we can add this and this. So this is the total load coming onto the beam. Okay, so this is 28.125 kilonewton per meter UDL. By adding the dead load in that, this is coming into the beam. But for the design, we will always consider the factored load, that we will always multiply by 1.5, and we will consider the extra one as per the design rules. So the factor maximum bending moment for the mid span we can directly calculate, because it is a simply like supported beam. Directly the formula for the UDL is WL square by 8. By putting that, we will get the factor maximum bending moment. So this is the factor maximum bending moment. So the effective depth we can calculate by reducing the clear cover. So we will get the effective depth as this. The moment of resistance for the RC beam MU limiting, we have seen this formula many times. We will again use that. By short downing this, it will be 0.138 FCK BD square. By calculating that, we got moment of resistance for our beam is 145, which is less than whatever the moment is coming onto the beam. Okay, so the factor maximum bending moment is greater than the moment of resistance of the beam MU limiting. Hence, the section must be designed as a doubly reinforced concrete beam. So now taking MU limiting as a MU1, moment of resistance restricted by single reinforcement RC section, then the remaining MU we have to design it by providing the external reinforcement into the concrete zone or the compression zone. Okay, so the area of the steel restricted by the single RC beam AST1, we can directly calculate this formula we know. So AST1 we got. The remaining moment of resistance required to be restricted by the beam is like MU total MU minus MU1. Okay, so this is 189 minus 145. Okay, so by that this is the extra MU we have to provide. So for that, directly we can calculate the area by MU2 divided by 0.87 Fy d minus d dash. So we all know all the parameters, and then by putting it, we got the AST2. So the total tensile steel is like AST1 plus AST2. AST1 we already calculate, AST2 we got it from here. So by adding that, we got the total AST. Taking 25 mm plus 20 mm diameter of the bar, for the extra requirement section, we will provide. You can provide it by your own way. Just this problem is solved by this way. So two 25 mm and two 20 mm diameter bars they have provided. So their total area, it is 1381, which is moreover similar to what is the total area is AST. So by this, when the section is WRC beam, the compression reinforcement can be calculated as follows. Stresses in the concrete at a center of the compression steel FCC is 0.46 FCK. We have calculated many times, which will be around 9.2. And the area of a compression steel in a given section ASC, also we have calculated. ASC ASC we have not calculated. ASC we can directly calculate like the similar way whatever VAST2 we have calculated. So for that we will consider MU2, but the down on the forces we will consider in only in a steel. So we will minus it from the concrete, and the lever arm will be D minus D dash 1 D. So by considering that the ASC we got it is 262.26. So we can provide 3 bars of 12 mm dia as a compression steel. So the total area of the compression steel will be 339. So in that way we can design. So this is the real problem and we have to design such a problems in a real life, because there they will not ask to calculate the moment of resistance. Rather than mostly the problem in this way, they will ask this is the type of loading is coming onto the beam, and this is already imposed load and this is the dead load, and then we have to design it. We have to provide the reinforcement requirement. So this is the main problem we can consider, like providing the reinforcement, and like here the depth and width is provided because constraint, so that is given, but sometimes we have to calculate that also. For that also there are formulas in the IS 456, and we can calculate like span by 10 to 12, in that range only the depth should be there, and there are ways to calculate the depth and then width. Okay, so any problem in this to understand? Like these formulas you have to remember. ASC, what in ASC we will at the down we will write FSC minus FCC in bracket D minus D dash, and for the calculation of ASC2 we will write 0.87 FY, because that is the normal one which is reaching the yield, but here it is like compression forces and compression forces in the concrete. So this we have to remember these formulas, and this we already have solved many times, so this has to be by hearted. Okay, then any problem in this? So the tomorrow class is also on the same time, like 6 p.m. in evening, and I will take the class for the tomorrow also. I don't know today only few students were available there, maybe because of Sunday holiday is going on, so never mind, we will meet tomorrow, and then we will try to solve the problems in the next TS session also. Okay, thank you everyone. Thank you Abhijit for attending this class. Yeah, so if you have any questions or any problem, then you can directly mail me on my mail ID, so I will try to answer it there also, or we can say into the next class also, no issue. So shall I close the meeting? Okay. Thank you everyone.